Alright, so the contents of this presentation will be divided into two parts. So first I'll give you the introduction. Second, the modeling of the cable stay bridge. I'll show you how we can use the wizard to quickly generate the cable stay bridge model. Then we'll see how we can build the nonlinear effects into the model. And then we'll see how we can determine the first initial cable forces through one of our method, which is called as unknown load factor method, which is built in MIDAS Civil. So first, introduction. So the common configuration for long span bridges would be like first, people go for balanced cantilever bridge where the spans are less than 100 meters. And if the spans are more than 200 meters, it's pretty obvious to go for cable stay bridges, which would be efficient for us. Whereas the spans which are like 100 to 200 meters, we can get a hybrid structure, which is a extradose bridge, where the cable inclination is very low. Whereas in a cable stay bridge, the inclination is almost 45 degrees. So we go for cable stay bridges when the main span is more than 200 meters. And these are some of the backspan to main span ratios that we generally use, something like 0.3 to 0.5 L. And the pylon height can be almost like L by 5. So these are generally followed principles for cable stay bridge. Coming to the major characteristics of cable stay bridge. So the main idea of cable stay bridge is like it should act like a continuous beam with a number of elastic supports with varying stiffness. This varying stiffness is caused because the length of the cables are different at different locations. That means it's a continuous beam that is sitting on elastic supports with varying stiffnesses. So you can assume it like that. So the behavior would be like a continuous beam. So all the members are predominantly under axial forces, where the cables are under tension. Both pylon and girders are under compression. So because the pylon and the girders are on compression, there could be second order effects that would be generated, like P delta effects. So that's why we cannot use a direct linear superposition, which is an influence line methods, to accurately capture, but approximately we can use those methods. So for long span bridges, the nonlinear characteristics will also influence the design, and nonlinear material properties like creep and shrinkage, which are time dependent effects of concrete, will also influence the design. So general arrangement of cables systems can be of three types. So first can be fan system, second harp system, and intermediate of fan and harp can be semi-fan system. So this is the overall design process in cable stay bridge. So starting from first determining the back span to main span ratio. So this generally we follow 0.3 to 0.5 of main span. Second, we determine the cable spacing. And third step, we determine the deck stiffness, like how stiff a deck should be. And then we determine the pylon height, which can be L by 15. And then we determine the preliminary cable force. So this is what we call it as final stage model, where you determine the preliminary cable forces through a method called unknown load factor, which is inbuilt in MIDAS Civil. Next, we go for the deck form, the selection of the deck, which can be concrete or can be steel composite or can be a hybrid structure. Then we perform the deck design. Then we do the construction stay analysis, which can be of backward or forward construction stay analysis. So we'll see all this process in detail in this webinar. And we use the different methodologies in construction stay analysis to get the pretension forces. Then we'll perform the static analysis and then dynamic analysis. So this process completes the cable stay bridge design. Starting from the modeling techniques, we can model a cable stay bridge in three types. First can be a spline model to accurately get the initial pretensions. For local analysis, you can go for multi-scale model or solid FEA model, where 3D solid elements can be used. Something like an anchorage location of a cable stay bridge can be locally analyzed. A stress analysis can be performed. So let's look at this example problem. This is a cable stay bridge. This is assume it as a general arrangement drawing. So we have these distances which are pre-assumed, and the tower height from the bottom can be 90 meters, and the main span is 220 meters. The whole length of the bridge is 420 meters. Let's take the bridge width as 15.6, considering it as two-lane structure. The pylon dimensions can be assumed in this fashion. First, I'll take the loading as self-weight, which is automatically calculated by the MIDAS civil program. Next, I'll assume some additional dead loads like railing and parapet loads. Third, we'll find out the initial cable pretension forces. These are the material properties that I'll assume for the sample bridge. These are some of the section properties. So I'll be only giving the area to the cable for the cable elements. For the girder elements, I'll give the moment of inertia as well, because they would be acting like a bending elements. And pylon, I'll give this area and this moment of inertia that I assume. So I'm directly giving the sectional properties, not giving the shape of the section. So let's start the modeling of the cable stay bridge through this wizard. I'll quickly jump into MIDAS Civil. I'll press a new file. I hope everyone is familiar with MIDAS Civil. So I'll start the modeling straight away. I'll go to structure, and here you will find the cable stay bridge wizard. This is how it would look like. So before that, let me add some material properties and section properties. You can add it from here in this dialog boxes. You can select the material properties. For now, I'll import it from another model. So I'll import all these material properties which are there in that model. I'm trying to import it to our model. So this is the cable material. The same table that I have shown you, those material properties have been inputted. Okay. So for cable, girder, pylon, and cross beam, girder and pylon. Similarly, I'll import the sectional properties. Let me change the resolution size. Okay, so that you can clearly see. Yeah. So I'll go to section and import. And similarly, I'll import the sectional properties, cable, girder, and pylon. So here I won't be specifying the sectional shape, the geometry, but I will specify the direct stiffness values here in the sectional properties. So for girder, I'll specify the area and the moment of inertias. So if you are not able to listen to my voice, if you have any disturbances, you can type in the chat window. All right. So now I have imported the sectional properties and the material properties. Now I'll click on structure click on Cable Stay Bridge wizard. So you have two options here, first symmetric and asymmetric. So this opens up so you can enter the other part and its dimensions. There's a bitmap image that shows, and all the nomenclature is written in this bitmap image, which you can follow to enter the values. Click on Symmetric Bridge. So A is the coordinate of this point, which is 0 to 25. So this is my bridge. So this is my point, and the pylon height is 90 meters. And the distances where the nodes and the connection of the cable to the girder, I already have those values predefined. So I know this value, so I'll enter the same thing in the wizard. So first A point is 0 to 25, and next is 100 comma 90, the B, the top of the pylon, and pylon height total is 90 meters. Material property, I'll select cable material property, the relevant material properties. For pylon, for tower, I'll select the pylon material property. Similarly, the sectional properties. Now here it will show you the deck shape. So you can turn on the percentage left slope and the arc length such that this curvature can be given. So here the distances, first let's start with 3 meters, and then the distance is 8 at the rate 10. So what do you mean by this? It's 8 divisions of 10-meter distance. And then you have 14 meters, which is this distances as per the GAD. And coming to the height, it starts from the B point. So this distance is 1.2, and after that it's a semi fan shape. So that's why these distances are variable. So 3 times at the rate 1.5 meter. So 3 divisions of 1.5 meter, it goes down, and then you have 3 times 2 meter, and then 2 times 2.3 meter, and last this distance would be 45 meter. So to cross check, you can go to drawing and click on update drawing. So this distance from the starting point of the cable to the deck, this is 45 meter, and from there it goes from in reverse. So it starts from the top of the pylon. Coming to the center divisions, you can enter the main span details. So the main span details are 14 meter. This is 14 plus 9 times 10 meter, then 12 meter, and symmetric. Similarly, I'll enter these details. It's 14, 9 at the rate 10 meters, 12, 9 at the rate 10, and 14. Alright, this completes the information about the model. And if you have any asymmetric bridge, you can select this and then enter the left and the right side details. I'll click OK. So you can appreciate how quickly we can generate the model here of a cable stay bridge. So manual modeling would be possible as well from this tab, but it would take a bit of time. So using this wizard saves a lot of time for you for a typical cable stay bridge model to generate. So I will be skipping the rest of the generation of the cable stay bridge. So what you can do is that one single plane model is ready. Now you can copy this to the other plane and create the cross beams and then the bearings and define the supports. So this wizard will generate only single plane geometric model, but it won't generate the supports and the construction stage details. So it only generates a single plane model. You have to perform manual operations to generate a full cable stay bridge model, something like this. So I'll directly open that model to save time. So this is there in our tutorial model anyways. Try to open this model. So I'll give you a glance how we have developed this model. So we have material properties which we defined in the previous model, same material properties, and then these are the support conditions. So I'll consider them as fixed supports, and the elastic links. So here there are bearings, and at the location where the girder would be sitting on the pylon, there is a cross beam and there are bearings, and you have rigid links which connect the girder to the top of the bearings. And then we have self-fight command which can be utilized from here, and then we have additional load. So I have taken 18.3 kilonewton per meter. Then there would be a sequence of pretensioning. So these two cables would form one set of pretension. I'll name it as tension 1, and for now as I don't know the cable pretensions, I'll assume them as 1 kilonewton and go ahead. Similarly, in pairs I'll apply 1 kilonewton. So you can right click and go to tables and quickly change the tension values or alter if you need. So these are the pretensions till 20 pairs on display. Now I'll run through the analysis. So here the element type for the cable elements is truss, and these are all beam elements. So let's see the element types first before going into unknown load factor method. So we have modeled the cable stay bridge for now. So in the MIDAS civil you have almost three element types to model the cables. First is truss element. This is a regular truss element which takes compression as well as tension. And we also have a dedicated cable element which is called tension only cable element. So here you have tension only element that you can select from this option, where it is subdivided into three options, which is truss. So this is similar to a truss which only takes tension, and we have a cable element, and this cable element is internally converted into two types based on the analysis type. First, if you perform a linear analysis, then the cable element would be converted to equivalent truss, where it will consider the sag effect of the cable. When you are performing a geometric nonlinear analysis, that time this cable element would be converted to elastic catenary element, where you can accumulate the large deformation and the large lateral stiffness and also consider the sag effect. So this is your truss element where you can give the tension and compression elements, and then equivalent truss element. So how you'll get the equivalent stiffness is through this formula. The program uses this formula to determine the K sag, which is an additional stiffness as the length of the cable or the pretension of the cable changes in a cable stay bridge. Its tension, its stiffness will also change. So this change in stiffness, the program will consider in an equivalent way, which is through this K sag formula. Coming to exact catenary cable element, catenary element, that time when you're performing the large displacement analysis, the program converts the cable element to this catenary cable element, where the geometric stiffness would also be included to calculate the stiffness of the cable element. So cable element would be treated as an equivalent truss in a linear analysis, but it would be converted to exact nonlinear elastic catenary element in nonlinear analysis. Coming to stiffened girder using SPC. So if you have any different cross section which is not built in the program, so you can directly import from AutoCAD through our SPC, which is section property calculator tool, which is available in MIDAS Civil. So now people generally ask us like what cable pretension will do to the bridge, like how do you find in MIDAS civil. So if you I'm just showing you a simple example where first you have this bridge but the pretensions are negligible, something like this type of bridge, which is a symmetric bridge, and you have the pretensions very negligible, and if you see the dead load bending moment, this is how it would be. There will be huge significant bending moments which is not a continuous girder, so there would be a positive bending moment at the cable and the junction, and there can be significant deflections, not like a continuous beam. So this is mainly because you get weak supports from cables where there's no pretension. But if you apply the pretensions, which causes high stresses in cables, so it supports the deck at these locations, which causes it to work as a continuous girder with the moment distribution as shown in the figure. So cable pretensions are very important to control the deflections and the bending moment in the deck. So this is what we call it as ideal state of cable strip bridge. So we need to determine this pretension forces for this specified conditions which we consider as ideal state. So for that we use unknown load factor method in MIDAS civil. So let's go to MIDAS civil now. So this is our model. Now as the pretensions are 1, so these pretensions are 1, I'll have ran through the model. Now I'll go to cable control and click on unknown load factor. So if I click add new, so this dialog box would come up. So you can give a name and you need to select a load combination. So before that we need to make a load combination. So this is what unknown load factor is. So this function optimizes the tension of the cables at the initial equilibrium position of the cable structure. So how it optimizes it will form a objective functions through these constraints, and then it will solve it through inequality or non or equality conditions, and then it will give you the unknown load factors, which are nothing but your cable pretensions. So this is one example, like if you have a bridge, a sample bridge where you have T1, T2 and T3 are your three pretensions, and there is a design load, and you give the constraint conditions something like this, like the uh, top of the pylon should move only 10 centimeters, or those conditions you give, and the program will find out, first form the inequality conditions or the equality conditions, and then it will try to optimize this through the unknown factors, and an optimization technique has been inbuilt in the program. So it uses that algorithm to find out the minimum solution which optimizes the objective functions. So there, first it will form the objective function types. So there are different types of objective function. It can be of linear, or can be square, or maximum absolute. So generally people can use linear or square or max absolute, where the results wouldn't differ much, but sometimes one of them would lead to economical pretensions, so you need to check them. And the sign of unknowns, the cable pretensions can be negative both or positive, so that you can select. So let's go to the program. So we need to first define the load combination. So here one load combination I can enter, and then select the self weight, additional load, and then the pretensions, giving the factor as 1 for now. Go to unknown load factor, and then select the load combination. Then you have this constraints. So to add any constraint, you can click on add. You can specify reaction, displacement, truss force or beam force. So you can specify the values, or you can also specify the inequality condition, something like upper bound and lower bound, giving a displacement of -10 mm and plus 10 mm. So this type of constraints you can specify. Here I've already defined some constraints which are my displacement constraints. So node 23 to node 45, node 23 to node 45 are this nodes. I'm giving the displacement constraint as an inequality condition of minus 0.01 mm to plus 0.01. Go to table. So this is my inequality conditions, the upper and lower bound. You can give in table format, or you can give through this dialog boxes. And then you can select the object function type as I showed you. So you can select linear, square, or max absolute. And then the sign of unknowns can be positive, negative, or both. And from this table, you have to select the tension forces, the load cases in which the pretensions are unknown. So I have selected all these are unknown, and then click on get unknown load factor. So thereby the program will give you the tension forces, the pretension forces for each load case, which is your set of pretensions for two cables. You can click on influence matrix as well to see how each pretension will influence the other values. So these are all the influence coefficients. So you can generate it in Excel file. So these are all the pretensions for tension till tension 1 to tension 20. I'll click on make load combination. I'll give a name. Click OK. Now I'll go to results. Click on deformations and check the deformations of LCB1. So LCB1, which has a factors of 1, that means the pretensions are 1. But whereas the output of the unknown load factor is a combination which has the pretensions as a factor. That means 1 into 1128 kilonewton is the pretension that is applied to the tension 1 elements, the cable elements. So first let's see LCB1 deflection. So you can see almost 0.39 meter is the deflection at 46 node without pretensions. Let's see the unknown output where the pretensions. So it's almost 0.01 meter. So this will satisfy the constraint conditions. The program finds this unknown load factors. So if you want to see the bending diagrams with the pretensions, so this is what the final stage analysis means. So now you got the pretensions, which are 1 right now here, but in load combinations you can see these are your pretension values. So if you want to apply them, so you have to copy it and paste it in the table of format to apply it as a tension loads here. Now let's go to another feature which is called cable force tuning. So this is also one of the important feature where it reduces the repetitive computation process to obtain the optimal cable pretension values. So it calculates the effects of cable pretension on the displacements and the forces, bending moment, shear forces through an influence matrix. So you can see an influence line and adjust some of the cable pretensions to get the desired result. So I'll show you how. So you can click on cable control, click on cable force tuning, select the unknown load output. So it's obvious that in reality you cannot apply 1128.85 kilonewton pretension in the site. So you need to round off these values as well. So that is also one of the reason to use this cable tuning options. So first I'll click on tension 1, and here I wanted to see the bending moment of the girder, of the entire girder. So right now there is no function. I'll try to add one girder bending moment function. So we do not have the girder group. I'll go to group, structure group. I'll select the entire girder. Then I'll go to cable force tuning. Give a name. Select the girder group, bending moment, my. And in the x-axis, I'll take the distance. Click add, close. So this is my bending moment. So this bending moment has been shown. So at the pylon location, it is a negative bending moment. So which is shown here. So you have a symmetric bending moment diagram. Now we can adjust this pretensions as per our need and see the variation of this pretension and its influence on the other bending moment change in the girder. So if I enter this as 1200, just a moment. I don't know why it got closed. Sorry for that, it got closed. Just a minute. Okay. Okay, so I'll give the girder group. Drag and drop. So let me create a result function. So I can adjust in this fashion and see the variation of the bending moment diagram. So I can enter those values. Okay, so you can adjust these values and turn on the influence value. So this shows the influence result. So this green line shows the influence of this particular tension in the change of this bending moment. So you can adjust in this fashion and then create a load combination, and then update to present model. Will update these pretensions. So now the pretensions have been updated as per the cable force tuning. So let's get to the next part, which is the construction stage analysis. So generally the construction stage analysis can be of two types for a cable stay bridge. First is your backward construction stay analysis. Second can be your forward construction stay analysis. So backward would go in this fashion where you deactivate the elements in a backward fashion, like a backward sequence of a real construction process. So you start with the pretensions that are obtained in the final stay analysis. So this would be your first model, and then you deactivate through different stages to reach the first stage. And forward construction stay analysis would be reverse of backward. So where this reflects the real construction sequence. First the pylons would be erected and then the deck would be erected in a sequence, and then it would be pretensioned. So it goes in this fashion. So the main drawback of backward construction stay analysis is it cannot accommodate the time dependent effects. It cannot capture the time dependent effects because the time dependent algorithms are incremental by its nature. So we have to use forward analysis in case of concrete bridges, long span concrete bridges, where the creep and shrinkage effects would be predominant. So the jacking force in backward analysis would be your truss force right before deactivating. So because we are moving in a backward sequence, whereas the jacking force in a forward analysis would be your right after activating. So that truss force you have to take as a jacking force. So the final pretension values and the pretension values which are in different construction stages will not be different, will be different. Why? Because each stage is different and each stage is changing, and there are different loads that are acting in each stage. So that's why the pretension values or the erection forces of construction stages are different. So we need to calculate them through construction stay analysis. So there are different methods to calculate them in MIDAS Civil. First, you need to simulate this construction stay analysis through our regular construction stage definitions. Then you can use one of our method, which is lack of fit force. So here the program will find out the additional force that is required for the truss to join this deflected shape of the deck. So we can get the lack of fit for the truss elements, which are nothing but your cable elements, and also for the key segment, which is considered as lack of fit force in beam elements. So I'll be showing you these features. So this lack of fit option is there in this construction stay analysis control dialog box, where you need to turn on this value, this options, the initial tangent displacement and the lack of fit force control. Then the program will give you the truss lack of fit force in a tabular format. So that is one lack of fit feature to determine the erection forces in construction stages. There is another method to determine the erection forces in different construction stages is through unknown load factor again. But here you need to simulate the construction stages and select the stages in which the cable pretension is, the cable is activated, that as unknown. Then the program will find out the pretensions in that construction stage or the erection forces. Let's consider this example. So we'll be seeing the lack of fit in a minute. But first, let's see the unknown load factor. Let's assume a sample bridge of this type of construction stages starting from CS1. So this is your first erect pylon and deck. Second stage is removing the temporary supports and apply pretension load to cable 2. And then you will erect the cable 3, and then you apply the pretension or the erection force, the jacking force. Install derrick crane and place the loads to the deck. Then you construct the additional deck. So here the wet concrete load of the next segment would be acting at this point, where it would create a vertical load and a moment. Next, CS6, apply pretension load to cable 1. Then cable 4 is installed and then pretensioned. Then the CS8, where derrick crane moves and place the loads to the deck. The next segment would be erected, then construct additional deck, then cable 5 and would be pretensioned. It goes up till here, till the right till CS13, where construct a support at the right span and place a second dead loads, which are your SIDL loads or crash barrier loads, and CS14 would be the right support jackup. So the red ones which are shown are my unknowns. So here I will be selecting the stage name as CS14, which is my final construction stage, where the constraints needs to be satisfied only in this stage. This is very important, where the constraints needs to be satisfied in CS14. For that, in each individual stage, what should be my erection force? That's what this unknown load factor in construction stage will do. So we need to select this construction stages where the cable is activated. So that would be considered as unknown. If you find two cables getting activated in each construction stage, in one construction stage, then you need to subdivide into two construction stages such that you can select those as unknown. So you need to select when the cables and key segments are installed, that as unknowns. And one more thing is, when you have creep and shrinkage, that time you cannot find the cable pretensions through unknown load factor directly, because the cable pretensions itself will cause creep and creep effects in the girder. So that's why program would require an iterative analysis. So for that time you can select this iterative analysis and give your iterations such that the program internally iterates the cable pretensions to achieve the final cable forces. So we'll be looking into this process. So this unknown load factor will consider the large deformation plus creep and shrinkage, and also the unknown load factors, which is the determination of erection forces in each stage. So we can include the nonlinear analysis in the construction stage analysis control dialog box. We can turn on this time dependent effects as well. So let's take this example, simple example, where you have 5 girders and then you have 5 cables, C1, C2 till C5. So this is the configuration of the final stage of an asymmetrical cable stay bridge. So the total pylon height is 30 meters. So these would be my material properties and the cross-sectional properties, some of the dead loads, and some additional load I'd be taking as 10 kN per meter. Next is the constraints of the unknown load factor calculation. So this constraints a designer has to determine first, because unknown load factor is predominantly dependent on this constraints, and it's very influenced by these constraints. So these constraints can be calculated in one way is where you can support the deck through your artificial supports. You can model one bridge. I'll show you a sample file. So this is our sample model where we can calculate in Excel the vertical segment load and the moment. So the segment lengths are given in this fashion. So we can directly calculate through the density of the concrete into area. Then we would obtain this vertical loads of different segments. Now to calculate the constraints for the unknown load factor, first you can create this type of model and give the supports where the cable is connected to the girder. That locations I'll give it as supports. I'll delete all the cable elements and run the analysis for the dead load and check my bending moment diagram. So I got a predetermined forces which should be there in the deck. So these are some of my limits which can be considered as a limits. So this can be taken as constraints. So you can alter as per your need, and you can also give the deflection of the top of the pylon as well. So for this sample I'll be taking this constraints conditions where I have done this preliminary analysis and got the bending moments. So now I'll go to MIDAS Civil. I'll open that model. So this is my model. So I have skipped all this construction stage definitions and the procedure. So this model directly has all these construction stages. Let me turn on the boundaries and the loads. So this is CS1, CS2. I have deactivated the temporary supports. CS3, CS5. Next segment is activated. Then the crane loads have applied as point loads. CS6, CS7 till CS12, CS14 where there is a jacket. So this is the final construction stage. I'll run the analysis. So here in different construction stages where the cable is activating, I'll be giving the pretension as 1 kilonewton. I can go to right click on tables. So here these are all 1 kilonewton. So I'll be running the analysis, and in the results I'll go to cable control, click on unknown load factor. So here I have given these constraints, so which I got from the preliminary analysis, this beam forces, these values of upper bound and the lower bound for the entire deck. And I've given the top of the pylon 106 node as this deflection limits. Now I'll select the final stage, which is my CS14 as my target stage where my constraint needs to be satisfied. And in different construction stages, the cable has activated. So the stage in which the cable is activated is considered as unknown. So I have selected them and click get unknown load factor. So the program determines the cable pretension of that particular cable element in that construction stage. So there are different cable pretensions at different construction stages. So you can see the influence as well. You can generate, and here you don't have the time dependent effects. So that's why mostly this pretensions would be accurate and would lead to a result where the constraints would be satisfied. But if you have time dependent effects, then you need to click on this iterative analysis such that the program will generate another model in the same folder where this model is saved, so which includes the uh, accurate pretension values. Click OK. So that's how you can determine the unknown load factors of each construction stage. So this is for the forward construction stage. So let me open one model where you have time dependent as well as large displacement, the same model. So here I have time dependent effects, creep and shrinkage as per CEB FIP, and compressive strength, and then I've linked to the deck elements, and I've given the pretensions. So this is a final model where the pretensions have been inputted. So let's see whether the unknown load factors will converge to 1 because the pretensions are already given. So I'll click on unknown load factor, modify unknown load factors. So almost they have reached to 1, but somewhere they are not converged. So that you need to click on iterative analysis and then the model would converge. So some of the constraints sometimes will not be satisfied because of this time dependent effects. So you have to be careful in selecting the set of constraints to satisfy and then get the required unknown load factor. So you have to tweak some of them and check your unknown load factors. So I'll be just touching upon the camber control. So MIDAS Civil gives you two type of cambers. One is manufacturing camber and the construction camber. So the difference is in manufacturing camber, the tangent displacements would also be considered, whereas in construction camber, it would be ignored because the formwork would be adjusted in cast in situ constructions. So we need to select construction camber in cast in situ, whereas for precast or prefabricated segments, we can go for manufacturing camber. So you can generate the graphs or in the tabular format, and you can apply this camber displacement to construction stages and check whether the level 0 is reached or not. So consideration of construction stage, creep and shrinkage, forward analysis, lack of fit will not be able to consider creep and shrinkage, but it will consider the large displacement. So lack of fit would be useful for steel bridges, but for concrete bridges you can go for unknown load factor where it will consider the both. So for steel, there's a distinction between a concrete cable stay bridge and the steel cable stay bridge. So creep and shrinkage, you need temperature gradient, camber control, the construction camber, temporary support, and cable tensioning in multiple steps. Generally, they don't do in concrete bridges, but that depends on the designer. So in steel bridges, they do it multiple pretension. So you can simulate multiple pretensions also in the program. So I'll show you the camber. So for camber, you can go to cable control, not cable, camber reaction, and click on general camber. Click on general camber control. Here you can give the construction direction. So here you have plus and minus. So I'll have to create two groups. So I'll give it girder plus and select these elements of the deck. Similarly, I'll select the other elements for girder negative. drag and drop. I'll lock it and go to General Camber, Camber Control, select Girder plus direction and negative X direction for Girder negative structure group. Click OK. General Camber, click on Camber Graph View. So for summation of the load of the construction stage load cases, I'll select summation. Just a moment. So the Girder group doesn't have the nodes. Try to activate it. Select all. So now it contains the node numbers. I'll activate, select all. Okay. So now you can see the manufacturing and the camber graphs for the negative and the positive Girder directions. So this is my construction camber. If you want to see the values, you can go to camber table. For the general constructed Girder negative, for the Girder positive. Alright, so this completes the webinar. So if you have any questions, you can ask me now. So you can type in the questions box or in the chat window. So if you have any questions. So one question, how to add cable properties. So you can go to properties, click on section properties. Here you can add the cable properties, section properties. So you can directly give the sectional properties or you can create from DB user. You can select round and then you can give a diameter of 0.5 and this would be the properties. If you have any other questions, you can type in the question box. All right, there are no more questions, so I'll be ending the webinar. So if you have any additional queries or you need support, you can visit our global support site, which is globalsupport.midasuser.com. So thank you so much for attending. Have a good day.